It's more complicated than that. Today's computers are pretty fast, so we can do a lot of hashes quickly. When I did the SHA 256 with the name of this course, it may have taken, I don't know, 1/100th of a second. So hashing with today's computers is really pretty fast. But that means it may be too easy to replicate blocks. So there's a new element that Nakamoto put in. And that is, let me go back here. In order to get a unique hash for this block, and to make it virtually impossible to replicate, I need to put some rules as to what that final hash looks like. So I can't just submit it to SHA 256 and get a hash. I demand that hash, the final hash, meets certain criteria. Because up to this point, we just hash, and the computers are pretty good at that. But this is where it gets incredibly complicated. Again, everything up to this point is deterministic. That is, I write algorithms, just recipes for solving problems, and I apply those algorithms to the underlying data. I create a batch. I then create a block. I put the block headers in. So everything up to this point is time consuming and computing power consuming, but there's nothing subtle about it. Everything is deterministic. If I do this, I get this. If I do this, I get this. This is where the deterministic nature of the blockchain fails. From this point on, it's no longer deterministic. What I say is, okay, for that final hash, for this final hash of this, the hash of block n+1, final hash of this block has to meet a certain criteria. Otherwise, it's too easy. And so here's the criteria as of this year. I want that final hash. Think about this. I want that final hash to start with 17 leading zeros. Now, if I just do a hash, you saw the hashes I did at the beginning. None of them even started with a zero. So what I want my hash to do is to start with 17 leading zeros. The probability of having a random hash start with 17 zeros is 1 in 100 quadrillion. So it's very, very unlikely. Again, the intent is to make it as hard as possible to create blocks on the blockchain, because that helps ensure the mutability of the data that is contained in the block. So I mean, this is a major point from going for those of us who are kind of have computer backgrounds. Everything up to this point is pretty clean. We can write algorithms and we can do everything we have talked about so far. Computer programs, computing power, and we do it. But now we have the requirement to create a hash with 17 leading zeros. The probability is 1 in 100 quadrillion. How do we do that? We had one more number. So we got our final hash at the top of the Merkle tree. But the probability of its having 17 leading zeros is virtually 0. So now we want one that has 17 leading zeros. How do we do that? And the answer is we have to keep adding numbers to it and rehashing. So this is why mining of a single block may take as much as 10 minutes. So we use that number that we invoke at this point, that we make up, is called a nonce. And the definition of a nonce is a word or expression created for exactly one occasion. So for this, we go back to in order to get this hash with 17 leading zeros, we have to take the Merkle root, add a nonce to it so that it provides 17 leading zeros. Well, if you were going to add one nonce, the probability is it's not going to create 17 leading zeros. Again, so we add a nonce and rehash. If we don't get 17 leading zeros, we change the nonce and rehash. If we don't get 17 leading zeros, what do? Change the nonce and rehash. So for those of us who are computers, so you cannot use an algorithm to create that final hash. All of this work results in trial and error. Say, what? Really? You got all this work and you resort to trial and error? That is, you take a nonce, see if it works. If it doesn't work, you take another nonce, see if it works. If it doesn't work, and you do that over and over again, trial and error, until you finally get a nonce that when you add it to the Merkle tree root, when you hash it to the Merkle tree root, gives you a resulting hash of 17 leading zeros. And it's really quite extraordinary. It's why it takes so long for blocks to be created, because the creation, the discovery of a nonce that actually gives 17 leading zeros is trial and error. This may be on a quiz. I'm not kidding. There's no way to calculate what the nonce needs to be to create 17 leading zeros. Just no way mathematically to do that. So the whole world becomes a world of trial and error. As a math guy, that seems a little crazy to me, that this whole world, I like to think of a deterministic world, a world where algorithms can be applied to mathematics and come up with solutions. And this whole world comes up with trying to find a nonce. And so literally what a miner does, remember, at this exact moment, there are 400 computer systems in the world trying to find nonces for the next block. So we've got a batch, gets distributed to these 400 nodes, and incredible computing horsepower trying to turn them into a block. And that means they do a whole bunch of stuff that's deterministic. That's easy. And then as the final step, you have to find a nonce that gives you a resulting hash with 17 leading zeros. So they choose a nonce and they hash it with the Merkle tree root. And then they check to see, do I have 17 leading zeros? Probably not. So I do it again, and I do it again, and I do it again, and I do it again. And eventually they find one. And they know they have the right one because when I hash it with the Merkle tree root, I come up with 17 leading zeros. That's easy. I can look at a hash and I can count the number of zeros. And if it's 17, I say, well, I finally found it. The probability that's going to be the first time is unlikely. So I have to keep doing it over and over again. So they keep incrementing the nonce and rerunning the hashes. So in the current Bitcoin network, they can run about 1 trillion hashes per second. So if you just stopped before the nonce, you could do batches very quickly. If you combine all the nodes, you get 22 quintillion hashes per second. It still takes 10 minutes to create a block. Why would it take 10 minutes to create a block? Because it's really, really hard to find that nonce. Again, coming into the nonce, you have the Merkle tree root. And the Merkle tree root is just a string of 64 hex characters. So you have no information about what kind of nonce will create a hash with 17 leading zeros. You have no information about that, so you just trial and error, trial and error. And it still takes about 10 minutes to do that.